0.01. You see? So I just substitute these 2 points to obtain phi prime, okay? And this is 15.03. And also phi t, this is a point, the attention now, this is a point Q, this is a point P. This is all this is equal to 15. Now, look at this. I want to bring this point Q just to coincide with point P. Why? Because I want the blue one. That's the blue one. That's what I want. Now what I will do, you see, I want point Q, in this case, coinciding with the point P. Now then, phi prime, okay, is 3, comma, attention now, 2 minus 0.1, because I want to bring this point to this point P. That's why you must subtract epsilon 1. So, in this case, observe that, you see, the variation of phi at P is equal variation phi prime at P minus phi of P. So, phi prime of P is just this number over here. You see? Because Q here, okay, I will set identical to P. So, since I add 0.01, from here to here, I have to subtract. That's clear. So, then I just substitute numbers. You see? This same point P, you see? This is 14.97 minus 15, which is equal minus 0.03. This sign here is this sign here. This minus sign. That's why you have minus sign. So, from here, look how easy I can substitute. Let's do as follows here. I prefer to write this here on this over here. See? Just to be, you see, this minus here is the minus over there, which I set over here. And attention now, J and K over here, you just look at J and K, are dummy indices, you see? So this relation here is the relation to start to reach the Noether current, you see, using Noether theorem. And also, I want to emphasize that this case over here is a particular case to obtain the Noether theorem. It's the spatial translation. You see, I'm using this relation here just to lead to the Noether theorem. You see, if for instance, I have, instead of spatial, time translation, the derivation is completely different. If I have a rotation, it's different. So, as I said, Noether theorem, okay, we can derive assuming a kind of symmetry. You see, if you don't do that, you don't reach any point where I want. So that's interesting on this, because on the final I compare, you see, in this conserved momentum, okay, is the conservative, the symmetry in which we are using the Noether theorem. And also I compare with the continuity equation in fluid mechanics. See that you see the analogy. That's it. That's a field, okay? Don't confuse this because I can use Noether theorem just in classical mechanics, okay? And this is Noether theorem whose focus is the fields. Okay? Fields, you see, these are important relation, again emphasizing just for spatial translation. That's it.